Hello, everyone, and welcome to phyloseminar.org. The current theme is the fossilized birth-death process, and this is the third talk in the series of 3 talks on that topic. Please use the YouTube live comment box to ask questions. Today's speaker is Dr. Joëlle Barido-Sottani. Joëlle did her PhD at the ETH Zurich under Tanja Stadler, then a 2-year postdoc with Tracy Heath at Iowa State, and will soon be a Marie Curie Fellow working with Hélène Morland at the ENS in Paris. Her main research interests are the development and use of birth-death models for Bayesian phylogenetic and phylogenic inference. She's also interested in exploring better programming practices for inference software frameworks to make them more reliable and maintainable. Welcome, Joëlle, and thank you for participating.
Thank you for the introduction, Eric. Hi, everybody. So like Eric said, my name is Joëlle. I'm currently in Paris, and tonight I'm going to talk about the fossilized birth-death process in practice and some of the applications of that process and some of the challenges that come with it. So I will just say that this is the third talk in a 3-part series about the fossilized birth-death process. So I think that it's a good idea to watch the other 2 talks before mine, because they give a lot of background and a lot of useful information on the FBD process. And obviously, I'm not going to be able to repeat all of that. So both of these are available on YouTube already. So I'm gonna give a quick outline of what I'm going to speak about. So first I'll just reintroduce the FBD process to remind everyone what we're talking about. And then I'm going to go through some of the practical challenges that you can encounter when you're looking to apply the FBD process to empirical datasets. And the first challenge I'm gonna talk about is how you place fossil samples on the phylogeny. Then we're going to discuss handling fossil age uncertainty, integrating all fossil evidence, and then I'll talk a bit about how you can integrate FBD with other models that have been developed for phylogenetics and how well that works out. And then I'll give some perspectives on where I see the FBD process going, I guess. So let's just start with some introduction or reintroduction of the fossilized birth-death process. So if you've watched the other talks, I guess you're becoming pretty familiar with the model. But just as a short summary, the FBD process gives the likelihood of a phylogeny that contains both extant samples, which are shown here in purple, and extinct samples, which are shown here in blue. And this likelihood is given in function of 4 parameters: the speciation rate or birth rate, the extinction rate or death rate, the fossil sampling rate, and the extant species sampling probability. So one thing to note is that the model is only identifiable is 1 out of 4 is fixed, so they cannot all be co-estimated. And what's usually done in empirical FBD analysis is that the extant species sampling probability is fixed, because that one is generally better known than all the others. So if we look at how the FBD process gets implemented in Bayesian inference, we're going to take a look at this complicated looking equation, but I hope I'll become more simple as I explain it. So this is simply the Bayesian, the general equation for calculating the posterior in a Bayesian inference, right? So the posterior is made of the probability of all the components of the inference in function of the data. And the specificity of the FBD inference is that here you can see that in the data we not only have a molecular alignment, but we also have fossil specimens. And in particular, we have fossil ages that come with them. And so the other components aren't changed. We have the likelihood, which is the probability of the alignment in function of the substitution model, the clock model, and the time tree. Then we have the probability of the tree model, what's sometimes called the phylodynamic likelihood, which is in our case the probability of the fossil ages and the time tree in function of the tree model, which is going to be the FBD process. And then we have all the priors. So this is how this is going to work in a Bayesian implementation. And currently, the FBD process is mostly used within 2 frameworks, the BEAS2 framework and the REF-based framework. And you can see the little logos on top of these frameworks. Okay, so this was a very short introduction. Like I said, if you really want to know more about the history of the FBD process and all the details that go into that, I would encourage you to watch the previous talks. But running the FBD process in practice, we encounter a certain number of challenges. And one of the first challenges I'm going to talk about is how we place fossil samples on the phylogeny. Because in a regular phylogenetic inference, obviously, the tree topology is built based on the evolutionary distances that are calculated between the samples, and these evolutionary distances are based on the molecular alignment. But unless you're talking about an ancient DNA analysis, which is not super common, you won't have such molecular sequences for your fossil specimens. So that only leaves you with the fossil ages, and that's obviously not going to be enough to place the fossils in the phylogeny. So that raises the question of how you're going to do that exactly. Now, the first way to do that has a very simple principle, which is to use the taxonomy to place the fossils. After all, most fossil specimens, they are classified in the taxonomy. They're assigned to a specific genus, or they're assigned to a specific subfamily, depending on how well the fossil is resolved, and so on. And within that same genus or subfamily, or other classification, you're also going to have other fossil specimens. And if you're talking about a crown group, you're also going to have extant species within that classification. So that means that you can constrain the tree to group all these specimens that are in the same, group together, and you can force that clade to be monophyletic, to have same common ancestor. And you can repeat that process throughout the tree and even have nested constraints. So here we have, the green genus that's nested within the purple subfamily, and so on and so forth. And if you add enough of these constraints on the tree, obviously you're going to limit very strongly the space of possible topologies, and you're going to be able to resolve your fossil placement pretty well. Now, the advantages of that approach is, first, like I said, fossils are usually assigned to a classification in a taxonomy as part of when they're discovered, when they're studied, when they're published, and when they're recorded in a database. So that's going to be data that is quite readily available. It's also the same data that would have been used to set node calibrations when running, previous analysis that used the old method of dating time trees. So that may be data that's even already, gathered as part of running a previous analysis. The additional advantage of using topological constraints is that there's no added cost on the inference because you're not adding additional calculations. You're not doing anything to the likelihood function. So it's not going to make the analysis run slower. It can in fact make it faster simply because you have less tree topologies that are possible. So you need to explore a smaller parameter space. It can create problem if the constraints are contradictory in some ways, but that's something you can easily identify because then the Bayesian inference is going to be unable to run or to find a proper place to start from. One of the big disadvantages, however, of this approach is that there's no accounting for uncertainty. Because, essentially a topological constraint, as I said, is saying that a clade is monophyletic, and that's a binary yes or no constraint. You can't have a clade that is, partially, that means nothing for a clade to be partially monophyletic. So it has to be either constrained or it's not constrained. And that creates issues that are, very quickly evident if you start looking at empirical data sets. So we see here the crown group of Cetaceans, and we can see if we look at this part of the figure that there's quite a bit of debate as to the placement of different taxonomy group in relation to each other. And so that's going to create issues when you want, obviously, to set topological constraints, because you can set a wider constraint on the entire Senrena family, but when you're going to start looking deeper into smaller groups, it's going to be unclear how exactly you should place them in relation to each other. And I might add that here we're looking at the crown group, but the picture gets obviously even more complicated when you're looking at stem groups, which are even more uncertain. So it's not ideal to have this sort of constraints that can't readily accommodate uncertainty. So there's another approach that is usually called the total evidence FPD analysis. And the idea behind that is to add morphological information on extant and fossil specimens. So you have, your regular molecular sequence alignment, which, as I said, is usually not available for fossils. And then you add to that morphological characters that are going to be available for fossil. Now, not all of them. Soft characters are generally also missing for fossil, but it's still possible to find an alignment there. And so this leads us to do a joint phylogeny inference using, for the morphological part of the alignment, a morphological clock model and a substitution model. And as I think April has mentioned before, the substitution model that's used is usually a version of the MK-Lewis model, which is essentially a GC69 substitution model that's been extended to an arbitrary number of states. And there are extensions of that model. I mean, you can partition your alignment by number of characters, for instance, which means that you put all the binary characters on one side, you put all the ternary characters together, and so on and so forth. There are also some ways to accommodate for ordered characters. This is something that we see, for instance, for characters that are discretization of a continuous character. If you've got a size of something that's represented as a character, it's pretty unlikely to think to go as a transition from very, very small size to very, very big size. Obviously, you're going to go through most likely all the intermediate steps. And so this is what we mean by ordered characters, right? You can only transition from 0 to 1, and then 1 to 2, and 2 to 3, and so on. You can't jump from 0 to 3. But if we take a look at our Bayesian inference, again, this is what it becomes when you're looking at a total evidence analysis. So you can see that on the data side, as I said, we now have two different alignments, a molecular one and a morphological one. And on the model side, I've obviously added also a morphological substitution model and a morphological clock model. And that gives us, a likelihood calculation that's not going to be split between the molecular likelihood and the morphological likelihood. But everything else stays the same, right? The FPD likelihood is calculated the same way. The priors, well, have the new models added into them, but they're not changed from that. Now, obviously, the total evidence analysis come with challenges of their own, and one of the big challenge is that morphological characters are a lot less nice to handle than molecular sequences. They're a lot less well behaved in general. And one challenge that's been mentioned by Rachel before is the size of the morphological matrix for practical reasons, and also because some fossils are pretty degraded. Some previous empirical analysis have been using morphological matrices that were pretty small, from, let's say, 30 to 50 characters. And we found in simulation studies that this is actually not a really good idea. And that this is not going to give good accuracy on the topology. In fact, when you have 30 characters on the morphological matrix, it's maybe even better in terms of inference to just use an unconstrained analysis, meaning an analysis that doesn't attempt to infer a time tree, but just infers a tree in terms of number of substitution. So this means that, you need Probably. I mean, we tested 30 and 300 in that study, and we found that 300 you had good accuracy on the topology. So probably the minimum number is somewhere between the two. There's another study that found that below 100 characters, there's a very sharp decrease in accuracy on the estimates of divergence times. So I would say the conclusion from that is that probably above 100 characters is a good thing to aim for when doing a morphological metrics. The second challenge that comes with morphological alignment specifically is the morphological model adequacy. As I said, they are extensions to the MK-Lewis that attempt to, account for a little bit more of the complexity that you see in morphological characters. And some people have found that models that account for ordering and, partitioning according to the number of states in the alignment have better fit than models that don't do that. However, there are also other evidence that having better fit as calculated by base factor does not necessarily equal better accuracy on the topology inference. So that's definitely something I think that needs more investigation, and it's going to remain a big challenge, I think, in using morphological alignments. So I guess one question that can arise from this whole presentation is, then what do you use, right? Which one is better, topological constraints or total evidence? Well, one thing first I will mention is that this isn't an either-or situation. It's totally possible to add topological constraints to a total evidence analysis. In fact, it's been done in previous empirical analysis. So that gives you a nice way forward, I guess. If you are unsure of some of your topological constraints, you can set the ones you are really certain about, and then go with total evidence for the rest of the fossils. But so we have attempted to study, whether you get better results on using topological constraints or using total evidence approaches. And so these are preliminary results that are shown here. Basically, we've tested a few different conditions. We tested what you get if you've got correct topological constraints. So you've got, exactly what correct constraints are. We've also tested imprecise constraints. So in that case, some of the lower level constraints are missing. So essentially, instead of having constraints, at the genus level, for instance, you only have constraints one level above that. Then we tested constraints that have errors in them, meaning in that case, we have a small number of fossils that are just assigned completely to the wrong clade. They're assigned to another clade picked at random in the tree. And then we tested total evidence. And so here are the results for the relative error and the coverage on the divergence times. And you can see that it doesn't seem to make a lot of difference which one you're going for, except for one outlier, which is when the constraints are wrong. So if you have error in constraints, that has a big impact on the divergence times. So it gets markedly worse estimates. Note that we're testing a pretty extreme scenario, I guess, in this situation, because more often in empirical situation, I suppose a wrongly assigned fossils would be assigned to a sibling clade, for instance, and not to a clade that would be, at the other end of the tree. But still, that confirms that if you have constraints that you're not really sure about, maybe it's better to go with less precise constraints than it is to make a mistake there.
Joëlle, I was wondering, what
Yes.
about encoding your constraints in sort of a total evidence type of way, like encoding them as a character that can be violated if there's sort of sufficient evidence? It seems like one might be able to do that.
I think it would definitely be possible. I'm not aware of any study that has tried to do that, but that could be a way to integrate sort of uncertainty in the constraints. Yeah, definitely.
There's, I don't know. I mean, there's one thing that sort of comes to mind is like the matrix representation by parsimony framework for super tree. And I mean, this is kind of like a bit of a super tree-ish sort of thing, right? Like you have the morphological tree and you have the tree that you're interested in, and you sort of want there to be some concordance. I don't know, just an idea of something that might be able to unify these two things.
That might definitely be something to try. Yeah, like I said, I'm just not aware of anyone who's who's tried to do that.
Cool.
Okay. So that's me done for placing fossil samples on the phylogeny. That's kind of one of the basic challenges of FBD analysis. It was mentioned, I think, a little bit in previous philo seminars on the FBD process. But like you can see, there's still some challenges that remain here, although the existing methods work reasonably well. Now, the next thing we're going to be looking at is handling fossil age uncertainty. Now, fossil age is estimated in a few different ways. There's relative dating, index fossils, absolute dating. I'm not an expert on that, so I'm not going to go any further into the details. But what all of these methods have in common is that they're not going to produce a point estimate for the age of the fossil. In all cases, they're going to give a range of possible values between a minimum age and a maximum age. You can see a representation of a few ranges here. So these are all ranges for North American mammals, fossils from the Mesozoic and Cenozoic that we got from the paleobiology database, and they're ordered by age of the fossil. So you can see that there is quite a bit of variation in the size of ranges, even for fossils that have about the same age. On the whole, there's a trend to have bigger ranges as the fossil gets older, which makes sense. But there's still quite a bit of variation there. And, this is just an example, but this is something that's going to be present in almost all empirical data sets. Now, there are a few ways to handle this age uncertainty in an FBD analysis. An FBD analysis, as originally configured, required the tips to have a fixed age. So that's what people have done, fixing the fossil age to a point within the range. And there's been a few different approaches to picking that point. Some people have used the median age, so the midpoint between the minimum age and the maximum age of the range. Some people have used the randomly sampled age for each fossil within the range. There's been others as well using the minimum age or the maximum age of the fossil for all fossils in the dataset. But there is also a second possibility, which is to sample the fossil age within the range. So in that case, what we do is we assume that the true age of the fossil is no longer data. It's also a parameter of the inference, and it's parameterized by the range for the age of the fossil, which is what is now a new data. And if we look at what that gives us in Bayesian inference, as you can see, if we look at this equation from earlier, there's been a few changes. We've now switched the fossil ages over to the model side of things in the posterior, and we've put the fossil age ranges as data. So that doesn't impact our likelihood calculation, but it's going to impact the probability of the tree model because we now have a new component, which is the likelihood of the fossil age estimates, essentially in function of the ranges. So the probability of the age ranges given the fossil age estimates. Now, in theory, that probability could be set to any arbitrary distribution. In practice, it's mostly been used with a uniform distribution, meaning that probability is 0 if the age estimates are outside of the range, which makes sense. And then within the range, all the point estimates are considered equivalent. So there's no particular weight given to any part of the range compared to another. But so that's a way to integrate the fossil age uncertainty essentially into the inference and to account for it without having to make decisions about where the fossil ages really lie within the range. And so we decided to study what difference these methods were going to make with the simulation study. I show here a quick look at what our simulation pipeline looked like. Essentially, we simulated trees under the fossilized birth death process with fossil samples. And then each of the fossil samples was assigned a real range that we got from the paleobiology database, so a range that was originally calculated for a real fossil specimen. And we also simulated a molecular alignment and a morphological alignment, and we did FBD analysis with all that. Now, the results were pretty striking, and that is that fixing the wrong fossil ages leads to higher relative error and low coverage on estimates of divergence times. It leads to higher relative error on estimates of diversification rate and turnover. And when we tried total evidence approaches, it led to higher Robinson false distance, and so higher error on the topology, and also lower coverage on estimates of diversification rate and turnover. So it's bad across the board, essentially, on every measure that we tried. Fixing the wrong fossil ages does perform really worse than sampling the fossil ages as part of the MCMC. Now, of course, if you have the true fossil ages, then you don't see any decrease in accuracy, but that's not something you can achieve for realistic data sets. And another thing that we found is that estimating fossil ages had a pretty low impact on inference performance compared to fixing the fossil ages, because that was part of the rationale behind fixing the fossil ages, is that adding this sampling component would make the inference lower. And we did find an effect. We did find that it was, I think, about 20% slower, but we expected something like, twice as slow or something like that. And it didn't happen. So definitely, based on those studies, my advice would be to sample the age uncertainty and really try to integrate that into the inference, because that seems to make a big difference on what happens. Now, an extension of that work is that we started wondering, because when you sample the fossil age, the point estimates of the age of the fossil become part of the inference. And so there is a posterior distribution that is produced for the estimate of each of the fossil ages. And we started wondering whether we could use that posterior. Now, for most fossils, the age range is short enough that that wouldn't necessarily be very helpful. But there are fossils for which the age is really badly known. And one example is the Baltic amber deposit that contains a lot of insect fossils. You see here a beetle fossil in amber and an extant representative of the same clade below. And this Baltic amber deposit is only dated to between 30 and 50 million years old, which is a pretty large range. So we again did a simulation study to figure out if we could use FBD analysis to reduce the uncertainty on poorly dated fossils compared to what is recorded. And so again, we've simulated trees, and in those trees, we picked a range for what we called our poorly dated deposit, which was comparable to the Baltic amber deposit. So we fixed that to the 30 to 50 million years range. And within that age range, some of the fossils were part of the badly dated deposit. So we didn't know anything about their age except for that full range of 30 to 50. And then some of the fossils, including the fossils that were outside of the poorly dated deposit, they were well dated. So they still had an age range, but there was a much shorter age range comparable to what we used in the previous study. And then we also simulated molecular and morphological alignment, and we did analysis this time in the RevBase. Now, the results are, it's possible to use FBD analysis to reduce the uncertainty around badly dated fossil ages. So we got better estimates in our study for poorly dated fossil ages compared to what you would get if you just picked an estimate by chance in the age range of the deposit. However, one caveat is that the accuracy was very strongly dependent on the proportion of poorly dated fossils compared to well-dated fossils. In fact, above 30% of poorly dated fossils, we basically did no better than chance. So I guess the answer to our original question would be yes, but you can in fact use an FBD analysis in combination with well-dated fossils to reduce the uncertainty on poorly dated fossils, but you need a lot of well-dated fossils to achieve that. So that concludes my section on handling fossil age uncertainty within the FBD process. And now I'm going to talk about integrating all fossil evidence into the FBD process. And that's quite an interesting topic as well, because it's one of the original promises, I suppose, of the FBD process, is that unlike using node calibrations that made use of only the oldest fossil in a particular clade, the FBD process would allow you to account for all the fossils in your data set. And that's been obviously partially realized, but there are still limits to how much fossil evidence can be integrated in the FBD process. One big limit is the computational cost, because within the FBD process, each new fossil specimen is integrated as a tree, so increases the tree size. And well, phylogenetic inference in general, not just with the FBD, are very strongly dependent in terms of cost on the number of tips in the tree. So adding new fossil is going to increase the computational cost very rapidly. One solution to that problem is to subsample fossils. Take a representative sample of all the fossil evidence that is available for a clade and run with that. So there's been studies on subsampling and that have shown that it can work really well, but picking a good subsample of fossils requires good information on the fossil placement in the topology, the sampling rate of fossils through time, and the structure of fossil sampling. So that might be information that is or is not available. Another alternative is to use the FBD range model that Rachel has discussed during her philo seminar. So I invite you to go look at that if you want to know more. But by integrating all fossils as stratigraphic ranges, so assigning fossils to species and then considering only the species, you can reduce the cost of running an analysis pretty significantly. And she's shown in her philo seminar that the performance is indeed a lot better when using the FBD range model. However, all of these two approaches rely on essentially leaving information aside, right? Because you're subsampling fossil, you're leaving some of the data out, and same thing for the FBD range model. And there's an additional issue, which is that not all fossils can be placed on the topology. There are fossils that are too small or too degraded to be placed very well within the taxonomy. For the same reason, they might not have enough morphological characters to be in a morphological matrix, or at least not with the number of characters that we said previously you need to get good estimates. So for these fossils, the only data we really have on them is their age. But that's still information, and that's information that ideally we would like to use. So one solution that's been proposed for that is the occurrence birth-death process, or OBDP. And if you look at the graph representation of this model, you can see that it looks very much like the representation of the FBD process, except for this one component that I have highlighted in blue, which is the occurrence rate. And what is an occurrence? Well, it's exactly what I was describing earlier. It's a fossil sample without topology information. So a fossil sample for which the only information we have is the date at which it was sampled. And so by adding this occurrence rate into the model, we are able to account for the number of these occurrences through time without having to integrate them in the tree, which we can't do because there's no information to place them in the tree. So this model is currently implemented in RefBase. And I can show you here an example of an analysis that's been run using the OBDP. So this is the lineage through time plot of the global Cetacea diversity in terms of number of genera through time as calculated by an OBDP analysis. And it doesn't find anything groundbreaking. It roughly matches with previous analysis, but really the key innovation is that here we're able to use a lot more of the fossil diversity that exists for this particular clade. So this is definitely a model that is going to undergo further development, and it's a very interesting approach to integrating, I think, more of the data that we have access to into, well, not exactly an FBD analysis, but an extended FBD analysis, let's say. So that's what I want to say about integrating all fossil evidence. I'm now going to look at how we can integrate FBD with other existing models. So one thing we can look at when we see the list of parameters of the FBD process is that we have the speciation rate and extinction rate that are sort of arbitrary variable, right? We assume that the speciation process and the extinction process are entirely controlled by these rates, that they're purely Poisson process. And that there's no, they're not the consequence or the result of other processes, right? They're here and they're entirely controlled by these parameters. But obviously in reality, speciation and extinction rates are things that happen as a result of other ecological interaction, you know, and spreading of species and things like that. And so there are ecological models that attempts to model that. And one model in particular is shown here, and this is the parameters it uses. So it uses environmental parameters, temperature and precipitation, and then it uses parameters that are related to the species spread. So how large is a species niche? How well can a species disperse in geographical terms? And then how long it takes to speciate following geographical isolation. So in such an ecological model, speciation and extinction are actually the result of a process. So if we look at the top line of this figure, you can see the speciation process. We start with the species that's occupying one geographical area, then it expands. And then possibly due to climate change, there's a fragmentation of that range with two populations that end up becoming isolated. And then as they keep being isolated, eventually they diverge, and this creates a speciation event. Similarly, we can see for on the bottom row, the extinction process. The species is going to expand geographically, and then again, due probably to climate change, it starts contracting. It occupies less and less geographical areas until it occupies none, and then that's extinction. So one question that we've wanted to raise is how well can the FBD process reconstruct trees that are generated under an ecological niche model? So that's basically asking, you know, how bad is our assumption in the FBD process that speciation and extinction just happen, and you know, can we get away with not modeling the processes that go into speciation and extinction? And our preliminary results, here we're showing the Robinson folds on the extant topology. So note that this isn't the Robinson fold on the full topology. We're just looking at how well we can reconstruct the tree of the extant diversity. And then we have the coverage on the divergence time. So again, for the extant species only. And so in both of the results, we can see that we are reasonably accurate, right? We have fairly good coverage for the divergence times. And well, the error on the Robinson folds isn't ideal, but it's still fairly small. So this is good news. It means that the at least for the extent tree, which again is what we're looking at here, there isn't really a big impact on the accuracy of the estimates that is made when we make this simplifying assumption, essentially, that speciation and extinction are driven by the rates instead of by more complicated processes. But this is definitely something that we want to investigate further, in particular look further as how well we can reconstruct the fossil topology, and whether there are other sources of variation in the ecological model that could impact how well we can reconstruct the trees that come from there. There are also other combined models that I'm not going to talk about in details, but I'll just mention that they exist. So we have an extension of the FBD process to the episodic FBD process, so with time-dependent birth, death, and fossilization rates. I don't think the episodic FBD process has explicitly been published as that, but this is the citation for the skyline birth-death process, which is just the episodic birth-death process that was extended to FBD. There is also an extension to the multi-type FBD process. So in that case, we have birth, death, and fossilization rates that are dependent on the state of a particular character, which can be a geographical character, morphological character, anything really that is set by the user. And we also have an extension of the FBD multi-species coalescent model, which combines a species tree that evolves under the FBD process with multiple gene trees that are accounted for under the multi-species coalescent model. And there are probably more that are in development that I don't know about. But that's also a good aspect of the FBD in practice, is that it's really being expanded to account for more realistic processes and more realistic data sets, because obviously the constant rates are going to be pretty unrealistic for most empirical data sets. However, and that's a little bit of a running theme, I guess, in this presentation, expanding the complexity of the models obviously comes with some challenges. And one challenge in particular is model selection. Can we actually distinguish between those more complex models and the regular FBD? And what's been tried so far is mostly model selection via the stepping stone method. And that's been shown to give pretty bad results. In one study, it was shown that it fails to select between the episodic FBD and the constant FBD. And by that, I mean it selects always the constant rate FBD. So this is an empirical study, so they don't actually know which one is the true model. But there's significant evidence for rate variation through time in that data set. So it seems pretty unlikely that the constant rate FBD would be the correct one here. And then that is confirmed by our own unpublished results, where we looked at the multi-type FBD this time versus the constant FBD. And in our case, this was on simulated data, so we know exactly which one was the true one. And again, it selects the simpler model as opposed to the correct one. Now, one paper has looked into an explanation for this and has found that the stepping stone method fails to account properly for the fossil evidence. And the proposed solution to that was to use reversible jump MCMC, which is a method that allows you to explore different models as part of the same MCMC inference. So instead of using a stepping stone or Bayes factor to make calculations after the fact on the marginal likelihood of a model, you integrate all of the models in the inference, and then you use the regular MCMC chain to jump between models and give you a posterior distribution for each one. So that's a pretty promising approach, but there are a few challenges again with that. The first one is the computational cost. Complex models already have an increased computational cost, obviously, because there are more parameters involved, more complicated likelihood calculations, and so on. But RGMCMC, on top of that, adds the fact that you expand the parameter space a lot, because every time you jump from one model to another, you have to explore the parameter space associated with that new model. So this is going to be, I think, continue to be, I think, a challenge in expanding FBD analysis is the computational cost. And the second challenge is the identifiability of more complex models. So there's been 2 papers by Luca and Pennell and other people that have questioned, whether the generalized birth-death model is identifiable, and they found that it's not. This is not affecting, I think, most empirical analysis that have been conducted so far under the FBD, because they use the regular FBD with constant rates, and models with constant rates are identifiable. The results from the Luca and Pennell apply to more generalized and more complicated models. And if you want to know more about these identifiability issues, I think they've been covered in the philoseminars as well, so I would encourage you to go and look there. But definitely, as we go with 2 more complex models and we increase the amount of rate variation that we attempt to integrate into our FBD models, I think we are going to run into those identifiability issues. So that's something to keep in mind, I think, for the future. Okay, so we're running to the end of my talk. I'm going to give some perspectives, not just on this phyloseminar, but I guess maybe on the whole series. I'm the last one, so I get to do that. So I think we've managed to convince, well, I hope we've managed to convince people that the FBD process is a really powerful tool for integrating fossil information into phylogenetic analysis. It opens up a lot of possibilities for phylogenetic analysis that weren't possible before. And, there's a lot of further extensions that are in the works or have been developed to better account for both the process of evolution, but also for biases or uncertainty that are found in empirical data. However, there are multiple practical challenges that remain. I've presented some of them in this presentation. Obviously, I couldn't be exhaustive, but there are others that I haven't discussed. The first one being biases in the fossil record. So there are biases in the way things fossilize. There are biases in the way fossils degrade with time and environmental conditions. And finally, there are biases in the way fossils are collected as well. And I think all of these biases so far have not really been accounted for very well in empirical analysis. And they could, depending on the data set, they could potentially affect results. I think another challenge that's going to be more and more present as well is the representation of output. A lot of the challenges I've presented turn around, including uncertainty that's coming from the data into the inferences. But there is also uncertainty that's coming from the Bayesian inference, and that needs to be represented accurately at the end of the inference. So far, I think most representations that have been adopted kind of reduce the entire posterior distribution to one tree or to one value. And there's a discussion here to be had to be whether this is the right representation, especially again as we go to more complicated models that may not be adequately represented by one single value or one single tree. And there are probably multiple other challenges that I'm not aware of or that I haven't worked with. That's it for me. I would like to thank a whole bunch of people I've worked with, that I've written papers with, that have given good advice on various things. And I'd like to thank the institutions I've been a part of and funding sources. Thank you very much.
Thank you very much, Joëlle. That was very interesting. And I appreciate you giving a bit of a wrap up there for everyone. I guess, can we kind of continue in that theme? First, I should encourage people to post questions. But can we continue in that theme and just talk about, like, if you really try to look, 50 years into the future or something like that, and obviously, like, there'll be some sort of computational analysis of fossils or something like that, or I mean, it seems like aren't the days of like individual people like looking and like coding individual characters on fossils? Are we going to be doing that in 50 years, or like will it be sort of like morphological analysis using like scans of fossils or something like that?
So I think, yeah, for some characters, I mean, continuous models is, or models for continuous characters, not something I've worked with. So, but Rachel has mentioned there's a lot of efforts in that direction as well. I definitely think that it's a promising avenue because it removes an element, I think, of bias or possible source of error, right? If you're simply measuring things or building for the most advanced techniques a 3D model of your fossil, then you don't have to have arguments about whether a particular feature is present or not, or exactly which category it should fall into. But I think a lot of morphological characters are also things like presence or absence of a particular feature, and that's not necessarily going to be as well, integrated into a continuous character framework. So I still think there'll be a role for manual coding of characters, if only to identify which features exactly should be measured, right? Because you can get a billion points of data on a 3D model of your fossil, but then not all of them are going to be relevant, or some of them are going to be strongly correlated with each other. So there's definitely still going to be an element of, an expert filter on what is relevant and what is not, I think.
How do you go about simulating morphological characters? I mean, that sounds tricky.
So we generally do it fairly simply, at least in my own studies. So we haven't explored really the impact of breaking the assumptions of the morphological model. So we simply run the MK Lewis forward. Yes, we've sometimes simulated a different number of states. In the analysis I did on poorly dated fossils versus well-dated fossils, we also tried to simulate some of the degradation that happens for soft characters, where some characters are only present in extant species, but not for fossil samples. But yeah, that's definitely an aspect I haven't really explored very deeply.
Yeah, it sounds interesting and hard. I mean, one thing you could try to do is just check to see, does the MK model give you some sort of summary statistics that are similar to the sorts of things that you see in real data. The Occurence model sort of, blew my mind. And I guess I'm sort of curious, like, could I imagine it as being, can you imagine it as being sort of a fossil for which you have absolutely no data, so that it just sort of like bounces around? If you were going to integrate it out, you would just sort of bounce around the branches of the tree at that time? Or should I imagine it as something completely different?
So it's basically separate. We're not trying to place it on the tree. Basically, you've got the tree on the one side, and then we use it's essentially using the volume of occurrence at a certain time as way to get an estimate on the global diversity. Because it doesn't tell you, a fossil for which you only have the time doesn't tell you what exactly existed at that time, but it does tell you that something existed, and that enough of that something existed to actually be sampled. And so by looking in variation, well, you obviously have to make assumptions on how the occurrence rate behaves through time, but by making assumptions about that, you can correlate the amount of occurrences you have to some measure of the global diversity. And obviously that's also going to impact what you see in the shape of the tree.
Okay, that's very interesting. Cool. Okay. Well, I don't see any questions, so I think maybe that's a wrap. Thank you again for your awesome talk, and I look forward to seeing where all this goes. It seems like a really interesting time in this field. Oh wait, yes. Let's see. There was one quick question.
Okay.
Yeah. So it's about RJMCMC. They're just curious how much it does implementing RJMC improve the topological and age estimates.
You mean using RGMCSC to explore between total evidence and topological constraints? I didn't get what the
Sorry. How much would you say that implementing RJMCMC improves the topological and age estimates? So, I mean, I think you were thinking of RGM CMC. Well, maybe you weren't, but I was when you presented it, I was thinking maybe you were thinking of it as more as a model selection.
Yeah, so that it's been suggested as a model selection tool. Obviously, if the correct model is a more complicated one, then using a more complex models, possibly as part of our GMCMC, should improve the topology and divergence times estimates compared to using a more simple model that would be less adequate for the data set. I mean, our GMCMC itself would probably not improve in and of itself, I guess, the topology and the divergence times. It's just if it allows you to integrate a more accurate model, a better fitting model into your analysis, then yeah, that is going to lead to an improvement.
Cool. All right. Well, thanks again. And I hope to see you around.
Thanks.
Bye.